Cool. Welcome back. Made it. Another day, another dollar. We're up. Yeah, we're live. Ready to go. So I wanted to start off, I went through some of the case problems. I didn't go through every one, but I wanted to get a sense of like where are we at right now. And I think overall everyone did a great job, like trying to take one of their first like weird engineering problems and turn it into like some actionable insights and some analysis. One of the things I noticed, a lot of people use like some kind, like either Python, MATLAB, or Excel to make their graphs, but there were a few people still using like hand-drawn graphs. And I haven't seen anyone do like a good hand-drawn graph in like 40 years. Like it's just, because you have to take out a ruler, you have to use graphing paper. It's very hard to have a hand-drawn graph that is accurate and represents like the equations that you're trying to show. So my suggestion is use Python, MATLAB, or Excel for graphs. I'm happy to give you like information about like how to plot, and if you know what you want to do but not sure how to do it, I'm happy to share code with you. And actually that Copilot assistant will like help you write code. If you tell it like, hey, I want to learn how to plot these equations, it will give you Python code that works. So there are ways to kind of work around it, and it's gotten easier and easier to like make cool graphics of engineering information. So that was one like overall thing, just a quick, like, make sure you're doing some accurate, like nicely made graphs. Then I wanted to grab like a couple examples and talk about them, and then also ask like, what do you see like where things could improve? So one group kind of took the idea of like, hey, it's 0.1 kilograms. That's about the size of a goose egg, so we're going to consider this a goose egg. And that's a great way to like take like a physics problem and turn it into like a real egg drop problem. And so I really like that approach, and it kind of set up like what analysis they cared about, and that's a nice way to do that. The thing where I saw a place for improvement is that when they talk about like the friction force, the fact that we need squeezing, that's where like it's a goose egg, there's got to be some number where if you press this hard, the goose egg will crack. So that's now the limit. And instead of using kind of vague like squeezing force, likely crush, look for any words like that. Like it's totally fine. The first draft, get your ideas down on paper, but then go back, take 10 minutes, anywhere you see words like likely or where else? Before, analyze each while choosing, more thoroughly. You don't need any of those. Replace that with some kind of quantifiable number. So for the goose egg, like if the number is 3 pounds, 3 pounds will crush a goose egg. And I made that up, but We can look it up, probably in a Wikipedia article somewhere, but put that number down. Replace the vague words with like quantifiable things. Good start. So quantify the work is the main thing. So this was n equals blank, whatever n they chose. Like if they chose 10 newtons, then 10 newtons. And then this crushing, when they're talking about like a crushing force, is it more than or less than? Less than, more than 10 newtons, as an example. Okay, so another thing, nice plot here where the team went through and made a position, a velocity, and an acceleration graph. The really cool thing here is they lined up all the x-axes. So time, you can see acceleration, position, and time all happening at the same time. You know, like when at 0.4 seconds, we can see a -3 meter per second velocity is a 0 position and also 0 acceleration, and all, at least for the spring, for that yellow curve. All right, so then the wrap up, they said spring seems to be most efficient, reducing in the shortest time interval, and then quickly slow down, remain free fall. I think this is meant to be like fluid. Quickly slow down and remain free falling at much slower speed. So again, going along, you get paid, as an engineer, you get paid for numbers. You gotta tell a story with numbers. You already did the hard work of like creating a model, integrating it, like creating plots. So instead of seems to be the most efficient and shortest time interval, spring reduces velocity to 0 in, and how long does it take? 0.05 seconds, something like that. At least just looking at the graph, when is it 0? And then here, instead of quickly slow down, we could talk about like what the acceleration is, if we want to say like how fast this thing decelerated. So instead of saying quickly slow down, fluid accelerates 150 to, or I guess I'll go bottom, like lowest to highest, 50 to 150 meters per second squared, and then remain free falling at, and I think, I don't know if, did anyone calculate what the free fall, what the constant speed was? No? You did calculate it, but I was just wondering if you like wrote that number down, of like, hey, this is the important one. I think it's around 20 centimeters per second. Not too fast. We're not doing like miles per hour. We're talking like, yeah, centimeters per second. And then don't mind it never stopping. So again, it's a theme here, right? Quantify the work. You did the work, trust your model. At least trust what you have so far for the model. There's always ways to improve. I know even at the very beginning when we were talking about like using a spring to stop something, there was a lot of hesitation of like, it's just gonna keep oscillating. And that's true, and maybe it's not physically true, but our model is accurate for conservation of energy. So if energy is conserved, then this is exactly what would happen. things might be a little different for other methods, but trust the work that you've done and just stick to it. Say something concrete and quantitative is the main thing. I don't expect everyone to do that right off the bat. Like, this is exactly where I wanted you to be, is like, just try something, do some analysis, and then try to connect it. So now I'm like trying to fill in the gaps of like where the numbers meet the words. Sound good? No one seems like, oh, I better write this down. This is great. This is exactly what I've been looking for as an engineer. This is gonna totally catapult my career into the next level. It will. Like, this is where you get paid this is why people hire engineers, because they can quantify everything. Like, if all they wanted was a whole bunch of like writing for writing's sake, then they wouldn't need an engineer. They would need someone else. But your job is to write something, but actually quantify, like, this is why this thing is better. Or worse, I don't know, whatever you're trying to do, mudslinging. All right, take a second, read this one, and I'll zoom out a little bit so you can see like their graph. What would you change, or what's your thoughts, or what would you change? What do you like about it? So take a second, read it, and then talk with somebody next to you. Share a thought. Okay, position, but reporting acceleration, but presenting position. Yeah, so we did that, like I was just doing it in class, and then we looked at Does anyone want to share thoughts so far? one thought that came up was acceleration is reported, but the only thing displayed is position. And that one, again, this is kind of like minor edits, but because technically if you have position, you can calculate acceleration, but it's not easy to see that. Maybe as an engineer, you can like look at a curve and be like, the second derivative is this because you dream in second derivatives. But for most of us, most normal people, we can't see the acceleration in this position curve. So that's like one, and again, it's a minor point, but one thing that's really great here is that they are quantifying, like they're using specific numbers that they pulled from their data to say, hey, look, viscous fluid has the best stopping. It has the highest acceleration, and if that's your number, then that's what you're reporting. Like you say we're looking for biggest acceleration, and there we got it. 147, tough to beat. 18 is much smaller, 10 times smaller, therefore 10 times worse. It's a pretty compelling story. So you make the case that we care about acceleration, you present acceleration, and therefore it speaks for itself, right? This is kind of the engineer's straw man argument. Have you heard of a straw man argument? Does anyone know what that is?
It's like kind of make up what the other side is saying and argue that.
So sometimes it's making up what the other side says. It could be that. Does anyone else have another interpretation of straw man argument? Or have you used it or heard of it before? No. All engineers. We know talk good. We do math. But straw man argument is the idea that you set up something. So sometimes it could be like you say that, like we all agree that something is true, and then people start arguing about that, and then you can make your points about something else. Numbers are a great way to like create a straw man argument where people start arguing over the numbers rather than the initial argument of like, if you went forth and said acceleration is our most important goal, here's the acceleration numbers, people start arguing over acceleration numbers, not the fact that you said acceleration is our most important goal. So with great power comes great responsibility. Choose wisely what you're gonna, because people do it both. Sometimes they don't even realize it. They'll present numbers like this, and people are like, well, that one's the biggest, let's go with that. And it's like, wait, that's not the most important. And now you're off building whatever, the next Elon Musk Tesla truck. Sorry, I skipped right over that. I was talking about this. Other things that you wanted to say? No one was like jumping out of their seat. That's why I just kept moving on. So I guess last things to say about this is like, just overall smaller deceleration. Just we're on a roll. Just report the numbers and let other people decide smaller or bigger. If you're really trying to make a point that this is much bigger, then you can use relative numbers of like 10 times bigger, 10 times smaller, 5 times smaller, and that's a good way of like quantifying but showing that you're trying to say it's smaller. And yeah, we'll try this one. Okay, one more example. Take a second, take like 10 seconds, read through. What do you see that like works? Do you see any room for improvement? What are you looking at to quantify? Like where are some gaps where you would see that you could quantify something? Okay. Yeah, you like laying out the equations.
Yeah.
Okay.
That's
Yeah.
very organized, very
Yep. Okay. Okay.
I think you're just saying, this is a lot. None of that is necessary, so what, it's just, this is what it is.
That works so well.
Oh, it's just so the abbreviation.
That's
I mean, they show like so they do have I explained that. Yeah, but I like the thought of like show me what you got. Yeah.
We're analyzing people's answers.
Okay. So
Differential equations. That equals B of N. Okay, then there's two walls, two U N. We have force of gravity. Acceleration is the second derivative position. Line up with those.
yeah, it's still pretty Yeah, I mean, you can get some. Because we have acceleration and velocity, the second one, we know it's sometimes okay. The first one, we know it velocity. Some kind of, the last one, we know it's constant. Acceleration. But yeah, this doesn't give us how, it's just what is natural.
Because that's what it says. Even when we're highlighting blue, it's the first one.
All right, so some ideas that came up, and I didn't mean to like hide this. It wasn't like a big reveal, but there is a graph of what they plot, like their solutions to those differential equations. But some of the thoughts were like if you're presenting these equations, since we're looking at specific m and k values, like it would make sense to like give those numbers of like what is this m and k, and because the like if we know these like in this case, we know position is going to be proportional to some like exponential decay. And in this case, we know position is going to be some proportional sine or cosine, but root k over m times t. So we know like natural frequency, but here we could report that, right? We could say like, here's the natural frequency for that spring. Here's the time constant for this differential equation. So that's a nice way to like present it and like add the numbers there. We know that first one is like square root of 1,000. The next one is 50. negative 50. So within 1 second, we're e to the 50, e to the negative 50 of like decaying velocity kind of term. What else? So we've got velocity versus time, and then we have these descriptions. What are the descriptions all? What's like a common theme in these descriptions? Is it describing velocity in each one? No, not directly, right? It does talk about like energy. So if we want to talk about, since we're saying energy, we could say KE, and again, here I use T, 1/2 mv squared, and that relates it to that velocity graph. So when v is 0, we have no kinetic energy. And this one, like, release, like, store and release energy. I would use like some kind of like quantify, like how much energy are we talking? Is this kilojoules or is this like millijoules? And for stuff, if it's 0.1 kilograms moving 3 meters per second, it's probably on the scale of like point something joules, like less than a joule, something like that. But it would be good to quantify that, like how much energy are we dealing with and how much do we need to get rid of? That is a great thing to say. So 1/2 times 0.1 times 9, so about 1/2 of a joule, rough number, but half a joule. We need to get rid of it somehow. Last one was just like kind of cool. A few people were asking like, what would it look like if we combined? So one group did go through the effort of combining the spring and the damper. This was not required at all, and you don't have to, but this is kind of what it would look like, where you have an exponential decay, but also oscillations happening, and then it settles at some like mg over k distance. So it's kind of the best of both, right? Like it slows it down, it brings it to some constant value. And usually this is what we do if we're trying to like stop something or slow something down. Add a spring, add a damper, call it a day. Start doing some tuning, like how much damping, how much spring constant. But here we weren't really like tuning anything. That one was just like, hey, cool, somebody did it, nice. It was fun. I just think they're neat. Differential equations. Perhaps. Other questions, comments, wrap up from case problem 1? Ready for the next one? Case problem 2 with a vengeance. We'll get to that next week. We'll get back to it. So then the upcoming thing is project 1, which is really like proposal for module 5. So project 1 is like choosing what you want to do. And since we're doing group work, this was my proposed process. This is what I think will work well. All right, so we'll work on some paper, actual physical paper. These out. Those. So module 1, we kind of introduce the basics of dynamics. There are forces, there's motion, forces cause motion. You already came in with some knowledge of like conservation of energy, impulse and momentum. So the general definitions of like how does motion happen, that's what we've been working on the past couple of weeks. Module 5 is a chance for you to apply the class to something that you care about. Like, it could be something for like a job that you want to get into, like a career that you're interested in, or if you're doing research or on club teams, and that's a great way to like spend a little bit of time and get some credit for like thinking about a problem, like what are the dynamics of the problem. So examples have been like in biomedical engineering, like a lot of people have been interested in prosthetics. So they're like, all right, well, let me look at the motion of an arm and I'll figure out what kind of motion I want and what forces act on an arm. Now I can figure out what a prosthetic would be. Like that's a great like module 5. It's not a thesis, like we're not gonna spend weeks on this. It's just a 2-week project where we're recognizing that there is motion and finding the causes of motion and then finding some way to describe that. We tried it already with case problem 1. So what we're doing today is first choose application or some kind of system, draw the free body diagram, draw the kinetic diagram. And that's the 3 steps. That's really the only 3 steps you need to get started for a dynamics kind of project. And what I think we should, so what I want you to do is like within the group is just submit, if there's 5 people in the group, submit all 5 pieces of paper. It's like we all had these ideas, and then when we get to module 5, you can either choose one or start mixing and matching. Or start all over. It's a brainstorming phase. Spaghetti on the wall. So first, yeah, go ahead.
I'm just lost.
All right, welcome back.
So like, what's like the prompt to this? Like anything? Like I just don't understand.
Like anything? It can literally be anything for module 5.
But
So
like what? Like, can you give an example?
So one, well, prosthetic was one example, but I already gave that example, so that's not going to help. So another example was someone.
We're gonna do this. How would you go about it?
Well, so like one example that was really cool was someone was, well, this part wasn't cool. Someone was rock climbing over at the center. They fell, broke their ankle,
Yeah, I saw that.
and recently?
Yeah,
This was a couple of years ago.
got rolled out.
Oof, man, that stinks. Okay, so this person, they couldn't rock climb anymore. They were very frustrated about that. But module 5 project, they wanted to figure out what happened to cause the fracture. So they did a free body diagram of like what happened as they were falling, what happened as they hit the floor, and figured out how much torque actually was on their ankle and related that to, and they even had the x-rays, so they looked at the x-ray and said like, oh yeah, this is where I would expect a break, and sure enough, there's a break right there. So that's another biomechanics example. Another one, what are the other cool ones? I'm trying to think. I'll come back to it. I know, yeah, there's more, but, because there have been a lot of like really cool projects. But it literally, it's just a chance for you to like think about the class and try to get something out of it, of like, this is what I think is important. So that when you're on an interview, so I'm imagining you coming up to the summer, or I guess like next summer. So you're looking for an internship. The person's interviewing, they're like, I see you took dynamics. We do a lot of dynamic analysis here at the company. What do you know about dynamic analysis? So instead of saying, I don't know, I got an A in the course. They're like, okay, well, everybody got an A in this course. Everyone who reached this stage got an A in this course. So your story is, So the last 2 weeks of Applied Mechanics 2, which is our engineering dynamics, I took 2 weeks to think about like what are the forces acting on a prosthetic arm. I made a model. I only used 2 degrees of freedom, but I thought that was enough to capture the relevant physics. And so I plotted the motion and then the resulting like normal forces that act on those joints. And now the person's like, whoa, this is the person we want for this job, instead of just like, they're just like everybody else. That's my goal. That's like, that's what makes me happy whenever people have like cool projects that they're interested in. So yeah. Short answer is yeah, do whatever you want. Long answer is do something cool. Like take some time and do something cool. Okay, but that's the 3-step. That's all we need as far as like deliverables for Friday. It's not even a full piece of paper. We're just trying to choose something, identify what forces are causing motion, and then define what that motion is. That's what we're doing. So causes and effects. Yeah. Have you seen physics problems where you pull well, it's kind of like a pulley problem, but the idea is it's like those big wheels, and then they pull a wire, pull wire off. Spool wire. So the question is like, if you have a spool of wire on the floor and you pull on it, you got to roll it towards you or roll away from it. You only apply force this way. It should see things fall down. Pull on the ball. It's going to go that way or this way. Yeah, and it's kind of an interesting question. And if you factor in like physical, like real friction, like is it going to slide or is it going to unroll but maintain contact? Yeah, so the spool, at least a lot of times when you pull on it, it actually spools itself up. Yeah. So yeah. Sorry. So do you have like general idea of things or applications that you're interested in? Okay. Yeah, like what's okay. Any okay. Yes, you could start with, you could say like, there's a bowling problem, if you care about spin and rigid interior spin, forward so you would use bowling on a wax floor, bowling floor, spin. I think oh, okay. Yeah. That could be cool. Do you want to do micro mechanics or like millimeter size mechanics or like the tread? Okay. Is that one? I figured that out. Okay.
was thinking doing ball screw and cable across machine.
You can't get really deep or you
And also, this is
yeah, like a description of what is the free body.
Yes.
and what's the plan?
Considering
Thank you.
I just have to do more of this stuff than like,
So what's the criteria? What's the
Okay, where's the free body diagram? Hey, what do you have?
with something, say, like, what is this supposed to represent? So like the example of bowling ball on a man. That's actually mostly self-explanatory. And then what forces act.
this is one for cannon or.
A cannon?
Can or can?
We can try it.
And ball on a cannon.
Alright, so we could say,
It's pretty cool. It's like, there's a lot of.
After we request the last
Okay, let's screw that.
not the first screw.
Would you describe it as normal? I mean, that's what it is essentially.
Yeah.
Yeah.
No gravity, and that gravity is on each one of those zones.
I try to do.
Is it friction or is it?
all right. So here's an example that came up. So people were trying to figure out like what to do. So let's get some practice like drawing. One, this is practice of just like drawing free body diagrams and free body diagrams. So cannonball, the cannonball motion. How do we draw a free body diagram on that? What forces are acting on the cannonball? We got gravity. Do we want to do point mass or rigid body? Like, do we care if it's spinning or not spinning? If we don't really care, then usually point mass is easier, unless someone has a strong feeling like, no, my pet cannonball always likes to spin. Okay, so we'll do point mass. So mg down, is that it? No? Yeah.
Whatever force is propelling it out of the can.
Okay. Is it so now we have a choice to make. Are we considering like what's happening while the explosion happens? Or are we considering what's happening after the explosion happens? Two different scenarios, right? At least to me, that seems like two different physical systems. So what do we want to do? During explosion or post-explosion? Post? Post-explosion? Okay. So does it have any thrust on it after the explosion happened? No? We have nothing like pushing it, right? Could be windy, so we could say there's a headwind or shooting into the wind, right? So does it matter that there's wind? It's just like, oh, the cannonball, no, it just goes. Wind doesn't matter. Sorry? It applies some kind of force. How do we factor in wind force? Like the wind, some kind of like air resistance. So we could have, if we want, we could say there's also some kind of force of drag, like opposing that x direction, of like due to the wind. Really, it's that relative speed. The cannonball doesn't care if it's going into the wind or with the wind. It's just how fast is it going relative to that. And then probably some kind of lot smaller, but there is, if there's drag going one way, there's also drag going the other way, but that one's relative to its like Y direction. What does our kinetic diagram look like? What kind of motion do we have so far? The weird way to ask this is, how many degrees of freedom does this cannonball have? Where degrees of freedom is just saying like, is it X and Y? Is it X, Y, Z? Is it X, Y, Z, theta, phi, and the other one? Like, does it have 6 degrees of freedom because it's a cannonball that's spinning and it's moving in a 3-dimensional space? Or do we want to like squash it down into something else? What's minimum for this one? At least based on the forces that we drew. 2? Yeah, 2. There's no, we didn't put any constraints on like the out of plane motion, but there's also no forces. Like, we're not considering out of plane forces. So it's okay to say like it's some kind of like 2-dimensional projectile motion, but I'm factoring in drag somehow. So if that's the case, the simplest way to do it is just, there's a Y component acceleration and an X component. And that's a totally satisfactory kinetic diagram. Like, I know there's 2 degrees of freedom, so I want to see both of those. Other ideas so far? What else are people working on? It's all just practice, yeah.
And for the robot maintain aid a few years back.
Yeah?
That picks up an inflatable rounded cube.
A cube, okay.
Where it has 2 sets of wheel pulleys that pick up and intake the cube.
So we have pulleys.
It's a really weird design that I'm drawing from memory.
Or I guess it was like some kind of cube, right? So something like this?
Somewhat.
Something like this?
Close enough.
Okay. Where like these belts. What we have like velocity of the belt on either side, so as the belt is sort of like spurring in, and we like grab something.
And there's an elastic at the back that keeps the 2 pulleys from getting too far apart.
Okay. Yeah, like some kind of support system, right?
Yes.
So one way we can think about this is like we have multiple moving parts. So we can look at it system, total system, but then also break it into individual systems. Because I can draw like just the block itself. The only thing moving it is force of friction from those like pulleys that are sort of pulling it in that way. Or like some, at least that's what I'm thinking. I'm imagining like
Yeah,
rubber
there's 2.
conveyor belts.
Yeah, there's 2. It's 2 independent gripping wheels basically that are on pulley systems connected to a singular motor, but the gear train has them moving in opposite directions, so they intake.
Okay, cool. And then we can also, so this one overall should have some kind of like mass times acceleration that way. And then we have some symmetry. If there's a force of friction pulling that one up, then there's got to be a force of friction pulling our belt down. So equal opposite. And then we could figure out like what are on these different parts, R1, R2, what are those reaction forces to keep the pulley like moving. And I probably like changed it around from the original design, but general idea there. Cool. Then on Friday, we'll try to wrap all of this up and make sure we have something submitted.